You know, there's this hidden code written inside every single one of us, right in our blood. For most of human history, we had no idea it was even there. But today, well, understanding that code is literally the difference between life and death. It's what decides who can save your life in an emergency and who can't. We're talking about blood types. I'm sure you've heard the terms, right? Maybe on a TV show or if you've ever donated blood. O negative, A positive. They get thrown around all the time. But what do they actually mean? Like, what is fundamentally different about my blood versus your blood? That's the mystery we're going to unravel today. All right, so here's how we're going to tackle this. First, we'll look at the code in your blood itself. Then, a quick history lesson on a Nobel-winning discovery. After that, we'll dive into your genetic blueprint, talk about why getting the right match is so critical, and finally, explore why all of this matters so much. Okay, let's jump right in. Section 1, the code in your blood. To really get this, you only need to know two key players, antigens and antibodies. Think of them as this incredible security system running inside your veins. So first, you've got antigens. Picture these as tiny little ID badges that are stuck all over the surface of your red blood cells. They're basically screaming, hey, I belong here. I'm one of the good guys. Okay, so if the antigens are the ID badges, then the antibodies are the bouncers, the security guards. These guys are floating around in your blood, and their whole job is to check those IDs. If they spot an ID badge they don't recognize, a foreign one, it's game over. They immediately go on the attack. So, let's put this into practice. Say you have type A blood. That means your red blood cells have the A antigen ID badge. Simple enough, right? This also means your security guards, your antibodies, are specifically trained to look for B antigens. They see an A badge and go, yep, you're cool. But if a cell with a B badge shows up, they attack immediately. And you guessed it, the exact opposite is true for type B blood. Your cells have the B ID badge, so your security system is always on the lookout for any A intruders. It's a perfect mirror image. Now this is where it gets really interesting. Type AB. These cells have both the A and the B ID badges on them. So because the body recognizes both of these badges as friendly, it doesn't bother making any security guards for them. Why would it? It sees both A and B as part of the home team. And then there's type O. These red blood cells are, well, they're blank. They have neither the A nor the B antigen, no specific ID badge. And because of that, the body's security system is extra cautious. It produces antibodies against both A and B. It's basically on high alert for any ID badge it might see. So you can probably see now why early blood transfusions were so incredibly dangerous, right? It was a total shot in the dark. But how did we figure all this out? Well, that brings us to a fantastic story about the guy who finally cracked this bloody code. Meet Karl Landsteiner. This Austrian doctor literally changed the world. See, before the 1900s, getting a blood transfusion was like playing Russian roulette. It might save you or it might kill you, and nobody knew why. But Landsteiner noticed something simple. When you mix blood from two different people, sometimes it clumps up. That one observation was everything. By 1901, he had sorted blood into 3 groups. A year after that, his students found the 4th one, AB. And for that, he rightfully won a Nobel Prize in 1930. He's the reason safe blood transfusions even exist. And believe it or not, it all started right here. This is a quote from a footnote, a tiny 2-sentence footnote in a paper he published in 1900. All he said was that human blood doesn't just clump with animal blood, but often with blood from other humans. That's it. That tiny little thought was the spark that lit the fuse. It was the very first piece of scientific proof that, hey, maybe not all human blood is the same. And that realization changed everything. All right, so we've got these different blood types, but where do they actually come from? Is it just random? Nope. That brings us to your genetic blueprint. Your blood type is handed down to you directly from your parents. It actually all boils down to one single gene, the ABO gene. And this gene comes in 3 flavors, or alleles, A, B, and O. You get one from your mom and one from your dad. The rules are pretty simple, really. A and B are dominant. Think of them as having a loud voice. The O allele is recessive, so it has a quiet voice. A or B will always be heard over O. But here's the cool part. A and B are co-dominant. If you get both, neither one shouts over the other. They're expressed equally. And that, my friends, is how you get type AB blood. And this little chart shows you how it can all play out. Look at that first example. If you have a type A parent who's secretly carrying that quiet O gene and a type B parent also carrying the O gene, their kid could literally be any blood type, A, B, AB, or O. It's a total genetic lottery. But then look down at the bottom. Two type O parents? Well, they can only have a type O child. It's a perfect, beautiful example of high school genetics in the real world. So genetics determines your blood type. But where this really matters is in the hospital. So let's talk about transfusions, and let's finally figure out what that little plus or minus sign is all about.
Okay, that plus or minus, that's all about something called the rhesus factor, or Rh factor for short. Just think of it as one more ID badge, another antigen. If you have this specific badge, you're positive. If you don't have it, you're negative. That's it. And right after A, B, and O, this is the most important piece of the puzzle for a safe transfusion.
And this brings us to the hero of the emergency room, O negative, the famous universal donor. And here's why it's so incredibly valuable. These red blood cells have no A badge, no B badge, and no Rh badge. They are completely, totally blank. That means you can give them to almost anyone because the recipient's immune system has no ID badges to get angry about. In a crisis, when you don't have time to type a patient's blood, O negative is the lifesaver. Now, on the complete opposite end of the spectrum, you've got AB positive, the universal recipient. A person with this blood type has the whole collection of ID badges, A, B, and the Rh factor. Since their body is used to seeing all of them, it doesn't make any of the security guards. There are no patrols looking for A, B, or Rh intruders. This means they can safely receive red blood cells from pretty much any donor. It's a pretty sweet deal.
Okay, so obviously, matching blood types is absolutely crucial for transfusions, but that's not the only time this stuff becomes a matter of life and death. For our last section, we're going to look at how this hidden code plays a huge role at the very beginning of a new life. I'm talking about pregnancy. You see, blood type incompatibility can be a really big deal, especially when a mother and her unborn baby have different Rh factors. If it's not caught and managed, it can lead to a really serious, even dangerous condition. The condition is called hemolytic disease of the newborn, and here's how it unfolds, step by step. Let's say you have an Rh negative mom carrying an Rh positive baby for her first pregnancy. Everything is usually fine, but during birth, some of the baby's blood can get into the mom's system. Her immune system sees the baby's Rh factor, flags it as a foreign invader, and starts building up a powerful army of antibodies against it. The first baby's already born, so no problem there. But the danger is for the next pregnancy. If that baby is also Rh positive, the mom's new, highly specialized antibodies can cross the placenta, get into the baby's bloodstream, and just start destroying its red blood cells. It's incredibly dangerous. But thankfully, and this is a huge triumph of modern medicine, we have a solution. A simple injection given to the mom can prevent her body from ever making those antibodies in the first place. So think about where we've been. We started with a tiny 2-sentence footnote in an old medical paper and ended with this incredible understanding of a genetic code that makes surgery safe and protects newborn babies. It's knowledge that has saved millions upon millions of lives. And it leaves us with a really fascinating thought for the future. You know, scientists are actually working on ways to just scrub the ID badges off of red blood cells entirely, which makes you wonder, right? Could we one day engineer a single universal blood type? One that just works for everyone and makes all these risks and complications a distant memory?